Good morning. The next topic we are going to see is elementary continuous time signals. There are several elementary signals which play a vital role in the study of signals in system. These elementary signals serve as a basic building block for the construction of more complex signals. These signals may be used to model a large number of physical signals which occur in nature. The standard signals and continuous time signals are unit step signal, unit ramp signal, unit parabolic signal, unit impulse signal, sinusoidal signal, exponential signal, and a complex exponential signals. These signals we'll see one by one. The first one is step signal. A step signal is a most important signal used for analyzing many systems. These step signals, the steps function is that type of elementary signal which exists for only positive time and zero for negative time. It for zero for negative time and only for positive time it exists. And so, if a step function has unity magnitude, then it is called as unit step function. The usefulness of unit step function lies in the fact that we want a signal to start at t is equal. If we want a signal to start at t is equal to 0, and so that if it may have the same value from t greater than 0, then we need only multiply this signal with the unit step signal. So that's if you multiply that signal with unit step signal, then you will get for t greater than 0, you will get a continuous value of 1. Unit step signal is useful for testing signals because the response of the system to unit step reveals the great deal about how quickly the system responds to sudden change in the input. The continuous time signal continuous time unit step signal u of t can be given as u of t is equal to 1 for t greater than equal to 0 and 0 for t less than equal to for less than and 0 if t is less than 0 if t is less than 0. Okay, then if unit shifted is shifted unit step function at u of t minus a is defined as u of t minus a for 1 for t greater than 0 and 0 if t is lesser than a. Next signal, unit ramp. Unit ramp signal has a unit slope. It has a unit slope. Its signal may be having amplitude linearly. It has an amplitude that varies linearly. It may be obtained using a formula R of t is equal to ramp. Since it is ramp, since here it is unit step, so u. Here it is ramp, so it is R. R of t is equal to t for t greater than equal to 0 and 0 for t less than equal to 0. And this is a graphical representation for R of t and R of t minus a. This is time shift. This is a time shift. Then R of t minus a is shown in here. Then rectangle pulse, the rectangle pulse or gate pulse. Rectangle pulse is defined as the rectangle pulse. Yeah, for these two values alone, from this to this value alone, you'll have output. Rest to the other values, the value will be 0. Okay, so x of t is equal to pi of t for 1. This is 1 for t minus t by 2 will t plus t by 2 will have the value of 1. For other all values, you have 0. So for time then pi of t is equal to 1 or 0 for t greater than half and 0 otherwise. Impulse function, as we know, only for one particular value alone we'll get 0. Here for 0 alone we have value is equal to 1. Whereas this is a, it can be 2, 3, 1. If it is 1, it's called as unit impulse. If it's other than 1, it's called as only impulse. So at 0 alone you have value. For rest of the other values you don't have any other output. And it has 0 duration and infinity magnitude. So x of t is equal to a, t is equal to 0 and 0 when t is not equal to 0. This is time shifted version. In sinusoidal signal, an example of periodic signal, it is a continuous time signal and gives a value, x of t is equal to A sine of omega t plus phi, where A is amplitude, omega is an angular frequency, and phi is a phase angle. Between each sinusoidal wave, t is equal to, this time width is equal to 2 pi by w. Okay, this is sinusoidal wave. It has amplitude of wave, phi phase shift of phi, and phase shift of phi, and time duration between two signals is t is equal to 2 pi by omega. Okay, exponential signal, it plays an important role in signal amplitude. There are two types of exponential signals: real exponential and complex exponential signal. Real exponential signal is given as represented as x of t is equal to a of e of at. A is a real and a is a real constant. Here we consider three cases. First case, we know which is the standard equation for real x of t is equal to a of b of t. First case, we consider a is equal to 0. If a is equal to 0, e power 0 is 1. So then the value is x of t is equal to a. This is standard as a constant value. If a is greater than 0, then if a is greater than 0, then we consider only positive values. Then the value x of t is, you get the x of t is equal to all these values when a is greater than value. Then the signal will exponentially grow. If a is less than 0, then we have negative values, and this the value will exponentially decrease. I'll show you. Okay, this is a is equal to 0. This a is greater than 0. It is a lesser than 0. It is exponentially decreasing, exponentially increasing. Then complex exponential signal. Complex exponential signal is given as x of t is equal to e of s of t. Instead of this s of t, you substitute as 2 plus j omega. So we substitute this value in terms of s, then you get this value, then multiply t inside, then you get e power the rho t into e power j omega t. Here again we have two cases where rho is equal to 0. Then rho is equal to 0 when rho not equal to 0, when rho greater than 0, when rho lesser than 0. When rho is equal to 0, then you have then x is equal to 1. E power 0 is 1, so anything will have a DC line. When rho is not equal to 0, then you have e power et. When not you have e power et. Then rho is greater than 0, then you greater than it have only positive value. So e power minus 80, this real term alone I'm considering. So e power 80 plus 2 per t, all this. When rho is equal to less than 0, then e power minus 80 plus 80 ut. All these values will get, then the graph will be like this. Here the graph will reduce, exponentially increase. So in the case, imaginary case, we use the second term in like this, p per j omega t. When and when rho is equal to 0, omega is equal to 0, and then you get x of t is equal to e power j omega t. Then if rho is equal to 0, omega is greater than 0, then you get x of t is equal to e power plus jt, e power minus 2jt, e power minus 3jt, e power minus 4jt, and go on. And then it will exponentially grow. Then when rho is equal to 0, omega is less than 0, then you get e power minus 2t, e power minus 2t. This signal will exponentially decay. So this is sinusoidal when plus j omega. This is when rho is lesser than 0, then rho is greater than 0. Okay, so this is the three terms. Thank you.